welcome to you students, and hello everyone. Welcome back to the Learn Daily Physics. And today you can see on your screen we are talking about ensembles. So we discussed statistical mechanics and we got its three branches from the statistical mechanics. One was the classical and other two was quantum, Bose-Einstein and Fermi-Dirac statistics. So now we will see what ensembles are. That to understand it is necessary to understand ensemble, because today we are going to move toward the statistical distributions. So when you will understand this ensemble, in these ensembles, in the canonical or in the grand canonical ensemble, we are going to make, in our next lectures we are going to make the partition functions, and from that partition functions we will calculate all of their state functions like enthalpy, entropy, everything. We can find everything from that partition function, and we can even calculate the molar specific heat. So it is necessary to understand this ensemble, what ensemble is. So let's see. Ensembles are generally the large number of identical copies of a system. Just like assume that first we read this one also, this definition also. So a system is defined by the collection of large number of particles. So these large number of particles, so the ensemble can be defined as a collection of number of macroscopic identical. Here it was a simple definition, and this definition is more informative, or you can say more better. So a collection of number of macroscopic identical but essential independent system. That that your system, if you look in this system, there are three kinds of system here. So number of particles are too much. Okay, one atom contain Avogadro's number of particles, and if there are a lot of atoms here, there will be a lot of particles. Okay, so let's see that there are two things in this definition. One is macroscopic identical and other one is essentially independent. What the macroscopic identical term mean? What here the macroscopic identical term mean? Let's see. That macroscopic identical term mean macroscopic identical mean that it will have same energy. Number two, temperature will be same. Number three, you can say concentration will be same, pressure will be same, okay, volume will be same. Okay, so let's try to understand this from an example, from a simple example first. That we have a classroom. So we have a classroom like this is our classroom here, and in our classroom we have same chairs. Just like in our classroom we have similar looking chair, they all are similar. So these are the chairs. We can treat, or we can use this analogy with ensemble, that the classroom is a whole system, And in this classroom we have subsystems. Every chair have same surrounding. This chair will have same surrounding, and the volume for the whole system for this chair will be same. As we consider this one also have the same volume, same temperature, same energy for all the system having, okay, that this system has 25 degrees Celsius temperature. So this will be at 25, this will be at 25, this will be at 25. The number of particles for the whole system will be same. Okay. One thing else, that if this chair, the probability of sitting of student, if you treat this as a state, then the probability of the particle occupying this state is same. In the classical statistics, we already discussed that in our classical portion. When I discussed you the classical statistical mechanics, I told you that the probability of getting particle any number, in that we write a postulate that any number of particle can be in the state or can occupy the unit cell. So any number means that any student can sit on this chair, any student can sit on this chair, or any student can sit on this chair. So from that analogy we can say that an this chair is an ensemble. This is just like this one, this one, this one. They all are the virtual copies, or in the case of chair they are the real copies. Okay. So let's have a look on a more specific example, that we have mainly. Now you understand what this macroscopic identical mean. This macroscopic identical mean they will have same energy, same temperature, same concentration, and same pressure and volume. Okay, but essentially independent system. Okay, but essentially independent system. As you know that in thermodynamics or in statistical physics, we mostly use gases. Okay, you can see also here I'm using a gas. Why we mostly use gases? Because they are independent. Less intermolecular forces are between two particles. So we consider them independent. They are not affected by the other. One particle here you see is not affected by this one. This one is moving in this direction, this one is moving in this direction irrespective of this one. Okay, so this is the independent system. They are essentially independent because that they are not affected by these surrounding particles. Okay, so mainly ensembles are of three types. I should have write three here. So mainly they are of three types: microcanonical, canonical, and the grand canonical. What is microcanonical? In microcanonical, you say this is an example of microcanonical ensemble, and in microcanonical ensemble, you can see here that in microcanonical ensemble we have an insulation, we have an adiabatic system here. You can say that no heat can enter or leave the system. If no heat can enter or leave the system, the heat is a form of energy, and this energy will not leave the system. And as it not leave the system, because of that, the system will retain its energy, and there will be no change in the energy, and energy will be constant. Okay, so this, and you can see here that the top of this flask is not opened, it's closed, and because of that no particle can go out, as in the case of this, as in this case. So no heat change, no volume change, and it is a closed system, and the number of particles will remain same. So an ensemble, so we can say that an ensemble in which number of particle, volume, and the energy mainly remains constant or remains constant, then the ensemble is called microcanonical ensemble. Similarly, like this, we can say that in this case we don't have an insulation here. There is no insulation as you can see here. So heat can move from this side to this side, and we can say that heat moves from, if this system is hot and the surrounding is cold, you know that heat moves from hot bodies to cold body, and heat will move from this body to this, and there will be a change of energy because heat is moving from some place to some other place, and the overall temperature will remain constant. Okay, so you can understand that heat moves from here and here, and it will be in an equilibrium and overall temperature will remain constant. Okay, so this was that energy is not conserved here. We don't have a constant energy. Energy can move from this way to this way, this way to this way, from in and out. It can move in and out, okay? But it is again a closed system, and in this closed system, you can see electrons, I'm saying electron particles are bound. Okay, these particles are bound, and number of particle is constant, so nv and t is constant, temperature, volume, and number of particles are constant here, but energy is not constant. Okay, we can write here that E is not constant. As you see in the grand canonical ensemble, we've opened our flask. When we open it, our number of particles can move in and out. We can put more number of particles from here, or our particles usually leave the system. So particles are not conserved now. Okay, so in this case we will have three things constant. One is mu. Generally, one is mu. What is mu? Mu is a chemical potential. We write mu as a chemical potential. You better write mu as a chemical potential. We will discuss later that when we will discuss this grand canonical. In our next lecture, we are going to talk about the canonical ensemble and its partition function. From its partition function, we are going to calculate its thermodynamic states. So the microcanonical ensembles are not usually very important for us because energy is conserved, everything is conserved here. So in this case we have to apply Maxwell-Boltzmann statistics because energy is not conserved. So we have to calculate that for a certain amount of as temperature is constant, so for a certain amount of temperature what will be the energy here. So this is important for us. We will discuss this one, and after that we will discuss this one. So then we will discuss that what is mu, what is chemical potential, when it is constant, when it is not constant, what is volume, what is T. So everything will be discussed there. So this lecture is very important for you to understand to move toward statistical physics, or you can say the statistical distribution. So if you understand canonical ensemble, it will be easy for you to make a partition function to understand the partition function. And if you understand the grand canonical ensemble, then it will be more easy for you to understand grand canonical ensemble and make its partition function. That the partition function is the function from which we can calculate everything. Okay, if we know energy, we can make its partition function, and from that partition function we can calculate everything. We will see how we calculate everything from that. So if you don't understand what entropy, what enthalpy, what everything it is, you better watch my first lectures from lecture before this lecture, starting lectures entropy and enthalpy, because in our next lecture we are going to use these terminologies. So those terminologies will be used, and if you don't understand them, you better watch my lecture, okay? So till then, assalamu alaikum, and see you soon in our next lecture.